Hello, AP Stat students. Mr. Eicher here. Going to look at a question based on a project that a few of my students did, probably 4 or 5 years ago, to review and extend a little bit of your thinking about two sample procedures. So let's get started. For their first semester project in AP Statistics, Shivang, Christian, and David were interested to see if the wording of a question could create bias among students at their school. They randomly assigned volunteers to one of two questions. Question 1 was the unbiased wording. Does the school need its own athletic facilities? Question 2, the biased wording. Knowing that the school can't currently afford such athletic facilities and could focus the money towards more practical projects, should the school create its own athletic facilities? 37 out of 39 responded yes to the first question, while 25 out of 41 responded yes to the second question. Before we look at A, maybe just point out that they did not have the same group sizes in their experiment, and that's okay. That occurred because of the random assignment that they used. They maybe flipped a coin or something that didn't guarantee that both groups would have equal amount, and that's not that bad of a problem, but thought I'd point that out. Part A, calculate the proportion of students who responded yes to each question and calculate the difference in proportions, question 1 minus question 2. So for question 1, we had a sample proportion that was 37 out of 39 believe the school needs athletic facilities, whereas our second sample proportion was 25 out of 41. So to calculate the difference in proportions, that would be p hat question 1 minus p hat question 2, which would be 37 out of 39 minus 25 out of 41, which gives us approximately 0.34 or 34%. So when asked the unbiased question, 34% higher, 34% more students think that the school should get athletic facilities compared to the biased question. Now that seems like it would be pretty significant. We're not sure at this point if we'd call it statistically significant, but 34% seems pretty big. But let's continue looking at this question. Explain in context two possible explanations for the difference in proportions in part A. So there are two explanations we've been talking about through this semester of why we would observe a difference as large as this one, 0.34. So I'd encourage you to pause the video and see if you can come up with those two possible explanations. One explanation, to put it very, very simply, is random chance. The subjects who received or heard each question would have responded in the exact same way if they had gotten the other question. We just so happened to randomly assign more yeses to the first question and more nos to the second question. So in this first explanation, basically what we're saying is we're assuming like there's no difference in the questions. The questions aren't really biased, or even if they are, it's not affecting people's responses. So they would have responded the exact same way if they had received the other question. So the reason why that we got this 34% difference is just by random chance. We just so happened to be unlucky in a sense, and we randomly assigned more of the yes people to the first question and more of the no people to the second question. If we had randomly assigned the questions differently, then this very well could have been flipped or could have been a different percentage, much closer to 0. So when we do a significance test, we're going to be asking how likely is a difference this large or larger just by random chance? Is it a likely explanation that you got so unlucky that so many yeses happen to be randomly assigned the first question? How likely is that? And that's what the p-value is going to tell us. The second explanation is this. The difference in proportions of 34% that we observed occurred because the second question, question 2, was biased, and it encouraged the subjects to answer no more than the first question. So in our First explanation, it's a random chance. The questions aren't really influencing people, and the difference we got is just due to random chance assignment. The second explanation is we got a difference as large as 34 because there actually is a difference in the questions, and the questions were encouraging people to answer a certain way. At least the second question had a negative nuance, right? That it's going to be too expensive to build fields. So people felt a little more obligated to say, no, I guess we shouldn't have athletic fields because of the cost. Part C, the researchers conjectured that the first question would produce more positive yes results. State the hypotheses that would be used to perform a two-sample z-test for a difference in proportions. To test this conjecture, define any parameters you would use. I'd encourage you to pause the video and see if you can write the null and alternative hypothesis and define the parameter. So really important to note again that we're working with proportions, so we should be using proportions here. We'll do proportion question 1 minus the proportion of question 2. That should equal 0 if there's no difference in the questions. Proportion of question 1 minus proportion of question 2. We'd like to see if it's producing more yes responses. So it would be greater than 0 and be more positive responses. And then to define the parameter, we would be defining what this is. And this is the difference in proportions. This is the difference in proportions, Q1 minus Q2, who would answer yes to the question. This future tense is really important here. You would not want to say who answered, past tense. That would be referring to the statistic. The parameter is, we can even include the unknown difference. We know the statistic is 34%, that's known, but it's the unknown difference in proportions, who would answer the question as a yes. So that was part C. Part D, we would like to know if these data give convincing evidence that the proportion of students like the ones in the study who would respond less favorably to the biased question compared to the unbiased question. But sadly, a condition is not met. Why is it not reasonable to use a normal approximation for the sampling distribution of p hat 1 minus p hat 2? Students will often ask when we check conditions, like what if a condition isn't met? And I've always said, well, the conditions will always be met if you're doing a 4-step process. In this example, this is the way the AP exam will get to the issue of what if a condition isn't met. So they're basically telling you, why is it not reasonable? Why is the condition not met? Specifically the normal condition. So I'd encourage you to pause the video and see if you can figure out, number 1, what's the condition that should be met, and number 2, why is it not met? So again, for our 4 conditions, we typically check all of these. We do not need to be checking these. So I put an X next to them. Maybe I'll just erase them because we shouldn't be checking those. That could confuse the AP reader if you start checking a bunch of conditions. Specifically, it's the N that's the problem. So the condition for the normal condition for a 2-sample z-test for a difference in proportions is this. Using p hat c, we would combine the proportions 37 plus 25, the number of successes I mean, and then divided by the total sample size, which is 39 plus 41, and that gives us 0.775. And we need both sample sizes, the n times p hat c, to be greater than or equal to 10. So if we did 39 was in one group, 0.775. Multiplying those, we get 30.225. 39 minus that is 8.775, which is not greater than or equal to 10. So the number of failures is not greater than or equal to 10. And we could do the same thing on the other side. 41 times p hat c. 41, 1 minus p hat c is not greater than or equal to 10. It's 9.225. So it's not appropriate. The normal condition is not met. since the number of failures in each group is not greater than or equal to 10. And the last part is question E, and this is kind of common on the AP exam. Anytime a condition isn't met, like we've seen in D, what E will do is do a simulation, and a simulation isn't based on having to use a normal curve. You can see roughly this is normal looking, but there's all these humongous gaps in between the values. So if we were to try to find an area under a curve, under a normal curve, it's not going to be a good approximation because a p-value might look like that, but you have all these big gaps in between, so the areas aren't really going to be equal. So what E says is, although a normal approximation cannot be used, it is possible to simulate the distribution of difference in sample proportions. Under the assumption that the null hypothesis is true, 10,000, that's quite a few, 10,000 values were simulated. So I've given you the height of each bar here. If you add all these up, that would be 10,000 trials, assuming the questions have no difference. So based on the results of the simulation, do we have convincing evidence, statistical evidence, that the second question does indeed produce biased responses? The main thing here is, what is our statistic? That's the first question. When given a simulation, what's the statistic? And the statistic specifically we're looking for is, what was the difference in proportions that we actually observed? We observed a difference in proportions of 34%. So once you know that, that's really pivotal to be able to answer this question. It looks like 34% is way out here. Here's 30. And this is a greater than, it's a one-sided test. So the p-value is going to be, the estimated p-value that we would use is 34% occurred twice out of 10,000 trials, which would give us a p-value of 0.0002. So do we have convincing evidence? We would conclude, since we have a very, very small p-value, it's less than any alpha level. I'll just pick 1%. We reject the null, and we do have convincing evidence. We do have convincing evidence that the second question produces biased responses among students similar to these. A couple points about our conclusion. I basically copied this last sentence for context and make sure that you use the language of convincing evidence. This is not proof. You wouldn't want to say, therefore the second question is biased. You say, we have evidence that the second question is biased. And also, produces, not produced past tense, but produces present tense. And the last thing I'd like to point out is this last part, responses among students similar to these. Since they were volunteers, we shouldn't say we can generalize to all students. We can only generalize to students who are similar to the ones in the study. So this was a 5-part FRQ. If you're wondering, would the AP Statistics exam actually ask a question like this? Yes, indeed. I modeled this question after a free response question from several years ago and just used this student data that was collected in a project for our context. So you could see something like this, where you state hypotheses, you say, oh, a condition isn't met, and then finally, we can get a p-value from a simulation, even if a condition isn't met. Thanks for watching this video. See you next time.